Hi, and welcome to our last video in our epic journey on covalent bonding. This is just a quick look at non-molecular compounds. So we'll be looking at covalent lattices, carbon nanomaterials, and covers the content as part of Chapter 8 in your textbook. The key knowledge that we need to be able to do here from the study design is understand the structure and bonding of diamond and graphite, explaining their properties, including heat and electrical conductivity and the differences in hardness, and also the structures and properties, applications of carbon nanomaterials, including graphene and fullerenes. Essentially, what you need to be able to do is compare and contrast these substances with other substances according to their bonding. Okay, so key thing here is to pay attention to the type of bonding and what that means for the properties so that you're able to compare and contrast this to other substances such as ionic compounds, metallics bonding, and even molecular bonding that we see in smaller molecules. So the key idea that we need to start with for this is the idea of allotropes. We know that elements exist in different structural forms. We have oxygen and ozone, which are different forms of oxygen bonded together. But we also know that carbon can exist as different substances. You may be aware already of things such as diamond, which is made of carbon, fullerenes, which are buckyballs, and graphite, and these are what we're going to look at. The different structural forms of an element are known as allotropes. And the differences between different allotropes in their properties we see purely as a result of the type of bonding that they have. All allotropes of carbon are made up of pure carbon, so they're elements, okay? Remembering that an element is something that by definition contains only one type of atom, then something that is made up of completely carbon will be an element. So diamond is an elemental form of carbon, graphite is an elemental form of carbon, as is fullerenes and soot. All these substances are pure carbon. Okay, so they're all made up of carbon atoms, but the way that they differ is dependent on how they're bonded together. So the key definition that we need to know here is that an allotrope is a different form of the same substance. Okay, so allotropes are different forms of the same substance in the same way that isotopes are different forms of the same atom, remembering they only differ by neutrons. When we come to have a look at explaining the differences between molecular versus non-molecular covalent bonding, molecular compounds are all the ones that we've looked at up until this point. So things like carbon dioxide, which is double covalent bonds between carbon and oxygen, water molecules, which have covalent bonding between oxygen and hydrogen. Any of these are discrete molecular compounds. That is, that we can write out the specific formula. We know that 2 hydrogen atoms and 1 oxygen atom will make a single water molecule. Okay, and if we were able to see them, we'd be able to count them. This means that, as we've just learned, we have strong bonds within the molecule. So there's strong forces within the molecule and weak forces between molecules, these being all our intermolecular forces that we've learnt about previously. This means that covalent compounds or molecules tend to have properties with low melting points. They don't conduct electricity because they're not charged in any way. There's no moving charged particles. So things like hydrogen gas, oxygen gas, nitrogen gas, all of these things are molecular compounds. Non-molecular compounds, though, are where we start to combine the ideas of both ionic and molecular compounds, in that we have large lattices that are made up of covalent bonds. Okay, so we've got strong forces between atoms that range right throughout a lattice, and there is no molecules present. Because we have a lattice structure, we see high melting points in a similar way to what we saw with ionic and metallic substances, and critically, that these are non-conducting substances. Diamond will not conduct electricity. The only ones that do conduct electricity is graphite. This is our exception, but non-molecular compounds such as diamond and silicon dioxide, silicon carbide will not conduct electricity. So the main ones that we want to look at are allotropes of carbon. So diamond exists as a network lattice, graphite exists as a covalent layer lattice, and fullerene exists as discrete soccer ball shaped molecules. These are the three ones that we need to be able to explain in detail that we're going to look at. So a covalent network lattice occurs when we have strong bonding in 3 dimensions. Okay, remembering it's a 3-dimensional lattice, so strong bonding in all 3 dimensions, and electrons are shared, so we've got covalent bonding. The bonds are tetrahedrally arranged around the central atom. So in the case of carbon, we're going to have carbon bonded to 4 other carbon atoms in a tetrahedral arrangement. And these will just continue to be bonded to 4 other carbons, forming a lattice as we go through. Every carbon is going to be bonded to 4 other carbons. Okay, so we form a large lattice arrangement. Diamond will do this, which is our allotrope of carbon. There are other examples such as silicon, silicon dioxide, and silicon carbide. And if you pay attention to the periodic table, you'll see that silicon is right under carbon on the periodic table, which is why it has such similar properties, because they're very close in the way that they behave. So this gives you a diagram of what some of these are. So we have diamond, silicon dioxide, and silicon carbide. These are covalent network lattices. Graphite is we're going to look at as a layer lattice, and we're going to look at that in detail as we move on. So the covalent network lattices, of which diamond is our key one that we're looking at, are non-conductors. They're very hard because of the strong covalent bonds in all dimensions of the lattice. Okay, and they have very, very high melting and boiling points because we have to break. There's no intermolecular forces here. They're all covalent bonds we need to be able to break in order to disrupt this lattice. So diamond is a giant covalent network lattice. Each carbon is surrounded by 4 other carbon atoms. This is a critical point here, which has a tetrahedral structure around every carbon. The 4 valence electrons are used in the formation of single bonds. So we have 4 single bonds to every carbon. And there's no spare electrons to enable electrical conductivity, and there's no charge. So these are diamonds are unable to conduct electricity. The bonding forces are extremely strong. We have strong covalent bonds. And this means that we have incredibly high melting points and boiling points. In fact, diamonds sublime, they go directly from a solid to a gas, but they don't do this outside of temperatures under 3,500 degrees, which is very, very high. In contrast, a covalent layer lattice has strong bonding occurring in 2 dimensions. Okay, this is critical, remembering diamond was 3 dimensions, with weak bonding in 1 dimension. So what this means is that we have layers where we have strong covalent bonds in the layer, and then between layers, we have weak intermolecular forces. Okay, so this is our 2 dimensions, X and Y, and then in the 3rd dimension, we're holding those together, we have weak intermolecular forces. Graphite differs greatly in properties due to this difference in structure. Okay, the arrangement of the carbon atoms is very different, giving it a different physical form, therefore it is an allotrope. You can see here, this gives us a diagram of what the layers of graphite look like, and you can see that there's no fixed bonds linking the 2 layers or multiple layers together. In contrast to diamond, graphite will conduct electricity, and it's slippery because those layers are able to slide over each other. If we look at the reasons why this occurs, we state that graphite is a giant covalent structure. In fact, it's often referred to as a giant covalent layer lattice or layer structure. In contrast to diamond, each carbon is actually only bonded to 3 others. So remember with diamond, we had it in a tetrahedral arrangement with every carbon being bonded to 4 others. In graphite, they form a hexagonal arrangement. So every carbon is going to be bonded to 3 other carbons, forming a flat hexagonal arrangement. So because they're only bonded to 3 other carbons, we'll get like a honeycomb structure. This means that there's 1 electron that isn't involved in bonding for every carbon. This electron is delocalized across the layer. Okay, so it's able to move freely throughout this layer, meaning that graphite can conduct electricity. Okay, so remembering the bonding is very strong within the layer, so we see very high melting points here, in fact higher than that of diamond. But there are weak intermolecular forces holding the layers together. This is why graphite in your pencil is able to skim across the paper, and the friction between the paper and your pencil grabs hold of one of these layers and lays it down onto the page, leaving a mark behind. Graphite, therefore, because of this unique property of being very slippery between the layers, is used as a lubricant in things like clocks and locks, where we have to have a dry lubricant where oil would start to gum up the system. So if we have a look here, this is our graphite structure. We can see that it appears hexagonal and then there's gaps between the layers. These gaps, we have weak dispersion forces, okay? So between the layers here, we have covalent bonding within the layer, and then weak dispersion forces, because this is non-polar because they're all the same element, between layers. The other type of structure that we need to know for our carbon is amorphous carbon. This is essentially, amorphous means non-structured. Okay, so it has no organized structure. We see this in things like charcoal, soot, carbon black, and which we use in things like copier toners. There's no structured arrangement to the carbon. Sometimes there are long chains, sometimes they're tetrahedrally arranged, but essentially we end up with just a matted arrangement of different length carbon chains. We use this for things like filters and for filtering out different compounds. It can be used for drug overdoses. These days it's used in modern cafes and stuff to give black buns and things like that. We tend to find charcoal being used as a dye in foodstuffs. Nanomaterials, when we come to talk about carbon, we're not going to do in much detail, but there are a couple of things that we need to pay attention to. This being Buckyballs, which are an arrangement of carbon atoms which have 60 carbon atoms arranged in a soccer ball arrangement. So they have alternating hexagons, 1, 2, 3, 4, 5, 6, and pentagons. So this means that, like graphite, fullerenes are able to conduct electricity because they have an unbonded electron. Okay, so with diamond and anything where we have tetrahedrally arranged carbons, we will not have the ability to conduct electricity, but any of our allotropes of carbon where the carbon is only bonded to 3 other carbons, we will see the ability to conduct electricity. So this is a small video that you can watch if you want, which talks about fullerene, as well as the different allotropes, graphite and diamond. The other nanomaterials that are particularly useful in modern research are carbon nanotubes and graphene. And these, much like fullerenes, have very, very similar properties in that we see electrical conductivity, and they're used for modern materials applications. Graphene is essentially a single layer of graphite. So we can see the hexagonal structure where we have each of these black dots representing a carbon. We have rigid covalent bonds in that single layer. It's relatively new, being only isolated in 2004, and is incredibly strong due to the strong covalent bonds throughout the single layer. It's being looked at for multiple applications in nanomaterials. Nanotubes have been in development for quite a long time and used in different drug delivery, superconducting materials and things like this in terms of research. They're closely related to graphene. They're a single graphite layer, but they're wrapped into long hollow tubes. You can have ones that are capped or non-capped, and they can be single-walled, i.e. a single layer, or multi-walled where you have layers within layers. They're only about 1 nanometer in diameter, but have incredibly high strength and can conduct electrical current because of that single unbonded electron. If you want to have a look at applications of carbon-based nanomaterials, page 186 and 187 in your textbook go into these in more detail, but we don't need to know this in terms of high amounts of details in terms of the scope of the course. Just want to point out quickly that there are other examples of network lattices, as I mentioned earlier, in terms of silicon. Silicon's group 4, so it behaves similarly to carbon and will form these large molecular lattices. These include silicon dioxide or silica, which is the main constituent of sand and is used in glass manufacturing. It has a crystal form. Crystalline forms of silica, much like crystalline forms of carbon, are found, and the crystalline form of silica is known as quartz, and you may be familiar with this. Essentially, you need to be able to summarize this bonding in terms of how they are similar or dissimilar to the types of bonding that we've seen before. Our covalent network lattices, remembering, have very high melting points, so they will be able to be spotted from molecular compounds which have low. And then when we come to comparing the other ones that have high melting points, such as metals and ionics, it's important to remember that they will have little to no conductivity in the solid state or the molten state. Because the melting points are so high, we don't tend to see them in molten state. So we can pick this up from being different to ionic, because ionic in the molten state, of course, will conduct. Graphite, on the other hand, we're going to look for that very, very high melting point and boiling point, will be good conductors in the solid state, and again, looking for that not applicable for the molten. That's it for our covalent network lattices and layer lattices. As I said, generate a good table, and you should be right with this, and I'll see you in class.